for various sort of monitor contexts, various sort of external screens. So Liskov substitution principle. I started covering it in the video, but I wanna make sure that this is really sunk in, because talking heads in videos sometimes make a little bit of an impact, even with colorful signs exhorting. Okay, so we have these contexts, right, where and this is, as it turns out, identical in its designation of the names. Okay, so the principle reflects the need to reason safely about subtypes when we're using polymorphism. And we can pass around an A as if it's a B. We want to be able to do so in a safe way, in a sane way. And this is the basic principle. And it sounds very fancy and lofty, but I'm going to try to communicate to you it's very practical, and it's essential to safety. It's essential to preventing bugs. So look, if there's something that we can conclude from the interface of B, something from the specifications, if there's something we can prove knowing the specifications of B, something that we can reasonably count on, that's the key thing. It says Q of X be a property provable about object X. But ladies and gentlemen, really this is about what could someone reasonably conclude about the supertype, the type T, right? So in this principle, they're calling B T and they're calling A S, okay? So if there's something that someone can reasonably conclude about the supertype, looking at its specification, looking at what methods it supports, looking at what those methods supposedly do, if they could come away with a conviction that this is going to be true based on the supertype, like that it's immutable, or that square root takes the square root of its argument, or that the counter can never decline, it can never go down, it can only rise. If they could count on these properties, on these features, based on reasoning about that interface, then if you want to declare a subtype of that type, which is incidentally one of the big advantages of polymorphism, we can extend our types over time. Years after we've defined B, we could define A and hundreds of other types that are subtypes of B, and all the code that will work with B still works with our types. So part of the open-closed principle. If we want to define these subtypes, then that same property that's true about the supertype has to hold for the subtype for this to be safe. Because if someone thinks they're dealing with a B and they're actually dealing with an A, then we don't want to surprise them. We don't want to give them a rude surprise that they think they're dealing with B, secretly it's an A, and it breaks their code because they're counting on it behaving like it should be like a B, but it's somehow different. That will be a problem. So the subtypes here have to maintain guarantees that someone could reasonably infer from the supertype. Okay, so if all they know is it's B and they can conclude this thing never changes, then sorry, anything you create as a subtype of that should adhere to that, or else they could be really surprised. Okay, and the situation here, which I presented, I think in that video, is we're have a developer who's creating code with a variable whose apparent type is one thing, but the actual type is something else. So here, the apparent type is C, but the actual type is D, right? And in order to make sure that for that code that's treating it as a T1, this code that's treating it as a C, doesn't break every time we create a new subtype, E of C, F of C, D of C, to make sure this code doesn't break, we need to make sure that what that programmer is counting on over here, treating it as a C, stays true. They're counting on these features of being C because that's all they know about. Maybe C is defined years before D. All they know about is C's, and they're counting on the features of C's when they're writing their code. The fact that it never changes, so they don't have to check again. The fact that it never declines, so they don't have to check again. The fact that it's always greater than 0, they don't have to check that again. They don't have to check it. Their code may be counting on this because it's a property of C, and if someone passes in another thing that masquerades as a C, it's as if it is a C, they need to be able to count on it. Basic intuition here. It's not just being picky here, it's basically common sense applied to typing to avoid bugs, to avoid defects. You don't want this code, which has been around for years, to suddenly break just because someone's defined a new subtype of C that doesn't happen to adhere to the promises here. If this code has been around, this is code written against java.object. Say C is java.object, right? It's the root sort of object in Java. And just because someone later defines a subtype that breaks that, you don't want it to break the whole Java library because it doesn't work with that subtype. So subtypes need to be consistent with their supertypes, is what this is saying, to avoid breaking code that was written knowing only about or with respect to knowledge of those subtypes only, right? We want to be able to extend our type systems over time with new types without breaking our old code. We want to be able to reuse this code, not re-break this code. Yeah. Object-oriented programming wouldn't have caught on if people talked about re-breaking as a big goal for it. Okay. So these interface specifications are contracts. They're promises. We saw contracts earlier for functions. Now these are contracts for whole classes or interfaces. Now I want to ask, who relies on a specification? So suppose we have this type C. Maybe it's a class. Let's for now we'll imagine it's a class. Could be an interface. But imagine it's a class. Okay, fine. Class or interface. Who's depending on that? What are the types of people that might depend on this?
Use the API, anybody who uses it.
Yeah, anyone who uses it. The people, as we say, programming against it. This foo is taking in a C, and presumably it's taking in a C in a way that's going to be a client of that C. It's going to call its methods, right? It's going to call Baz and Zap on C. It's going to call, do X on C, right? It's a client of C. It's using C, right? So that's the clients of an instance of C. The other party that might use this information, and then when you call a method, do X on C, you call Zap on C, you're referring to the definition of what Zap does or do X, right? You're a client of X. You want to know, what does this do when I call Zap? What does it need for an argument? What are the preconditions for it? What does it return back? What does this square root thing take? Which argument is which for it, right? We're a client of C, eh? So that's one group that uses that information. But another group that uses that information are the people who create subtypes of C, right? You're creating a D. You're creating a subtype of C that could be passed around as a C. That's what Java gives you if you create a subtype. Those people also need to know about these specifications, right? And it turns out that there's another class we'll get into, maybe next time, depending how far we get today, maybe next week, next Tuesday. There's another group that actually use the code that are tied up, and that has to do with people who are actually superclass creators because of an overriding issue. But you don't have to worry about that right now, okay? Now, if C is not defined, I've got to overhaul this to use consistent thing. If we never define a specification for C, this doesn't help. Because people are going to come to conclusions without a clear specification. There's going to be guesswork. What really benefits is if C has a clear specification of what you can assume and what you can't assume, and then people who use it can be clear about that. That helps people who are creating these subtypes. If you're creating a subtype and it's not clear what the supertype does, the situation is considerably worse, and you might even choose not to use it as a subtype. Okay. Now here, our focus for the entirety of today's lecture in Liskov substitution principle, this is all about promises. It's all about what promises can D make legitimately to be consistent with the promises of C, to make sure it doesn't break code that's counting on a C. Okay, this is what we're going to be talking about. And the metaphor that I gave was one I introduced 2 times ago, but it was more fully fleshed out in the video, which had to do with this franchise. So, okay, you're setting up a FedEx here in Saskatoon, and for it to be a legitimate FedEx, if FedEx says you have to deliver your package by 12 noon for delivery 5 p.m. the next day in Toronto, what is your franchise allowed to do? There are certain things it's allowed to do and certain things it's not allowed to do to avoid causing customers enormous grief. So given the parent company guarantees, the guarantees that FedEx provides on its website, what guarantees must your franchise give to be legitimate? And we talked in the video about preconditions as well as post-conditions. So in a parent company, if it says you have to drop off the package by noon, the franchise could say, for my franchise, I allow a loosening of this. Because someone who looks at the website, comes in assuming the deadline is noon, they're not going to be disappointed, right? They're getting in at 11:59, and you tell them, look, sit back, relax. We allow here up till 3 p.m. delivery, and they'll say, oh, okay, great. They're never going to be rudely surprised. They're never going to feel violated. They were counting on this, and you ripped them off. You went to, they went to your franchise, FredX instead of SamX. And because of that, they feel ripped off because they walked in your door at 11:59. And imagine this, that you told them, sorry, in FredX, you have to deliver the package by 9 a.m. They'd say, you're not FedEx, you're a fraud. You're not a real FedEx. You're a fraudulent purveyor of courier services. You should take the FedEx logo down. Because I came into counting on the promises made by FedEx on their website, and you're telling me for your store it has to be delivered by 9 a.m. It's 11:59, and I don't have time to get to SamX, and I'm screwed. This would be a bad situation. That could make a customer legitimately have great complaints. Do you agree? This is violating their trust. This is violating their reasonable expectations. Do you agree? And in a programming context, this causes a defect. That someone's counting on this thing that they're reasonably counting on, and it turns out it's not the case. So this is our preconditions. We can loosen preconditions. In other words, we can accept a much broader set of preconditions. Here, the set of possible times you could come in for FedEx are those those before noon, right? Before 12 noon. They probably allow equal to 12 noon. And what we can do is we can loosen this. We can allow a broader set, less than or equal to 3 p.m. of possibilities for when you come in. The preconditions can be broad. And what we can't do is say, well, for our FredX, we'll only accept those if they're in by less than or equal to 9 a.m. That's a subset of those less than or equal to 12 p.m. And we can't create a strict subset. Does that make sense? So we can loosen preconditions, right? For postconditions, what can we do? If you've watched the video, you should remember this. What can we do for postconditions?
Strengthen them.
Yeah, we can strengthen them, and by strengthen, okay, this is screwed up. For postconditions, we can actually make them more constrictive, more specific. So if the parent company, if for FedEx, they say delivery is guaranteed by 5 p.m. the next day, we, as FedEx, could say, you know, we can actually guarantee delivery by noon the next day. Because how are they going to be disappointed, right? If they're counting delivery is going to be tomorrow by 5 p.m., and you tell them, well, actually here we guarantee delivery by noon, that's still fine because that was within the set of possibilities, right? So this is the precondition here on the left, and we'll imagine a postcondition here. And the postcondition here is, you know, parent company guarantees delivery sometime less than or equal to 5 p.m. next day, right? This is sort of delineating this set, is delineating the set of possible times. And put aside the fact that it's a continuous set the next day, okay? We're mentioning it's discrete times. And we can, with the postcondition, say, well, for our FredX, we actually guarantee delivery by less than or equal to noon the next day, delivery. This is postconditions, right? And they can't be disappointed because after all, that's within the time frame that was guaranteed by the company, by FedEx, but it's more specific and it's a subset of those times. We could also legitimately tell them, as FredX, we actually will guarantee delivery between 11 a.m. and 12 noon the next day. In other words, within the hour up till 12 noon the next day. We could say, in fact, we could say all packages are delivered tomorrow, and I'm going to put aside the continuous discrete thing. All packages are delivered tomorrow exactly at noon the next day. Can they object? No, because that's consistent with FedEx. Fed says by noon. So, okay, so they're all delivered at noon? Oh, that's kind of strange, but yeah, sure. I mean, it's still by noon. Okay, right? So postconditions can be strengthened. Preconditions can be weakened. Any clarification on that issue? Okay. So, you know, here's our FredEx franchise here, right? We have two franchises, and some might be legit, some might not be. So this one here, how about this FredEx franchise one here? Is this legit? The precondition. So for FedEx is all, the package has to be delivered by 12 noon, and the postconditions it's delivered by 5 p.m. the next day. For FredEx franchise 1, the package, so is this a legitimate franchise? Something where the package for the precondition has to be available by 3 p.m. rather than 12 noon, and can be delivered it's guaranteed to be delivered by noon the next day. Is that okay? Sorry?
Precondition package available by,
Yeah, by package available, I mean it has to be delivered by the customer to the FedEx, yeah. How about for FedEx franchise 2 here? Package is delivered by the customer by 12 p.m. and the package is delivered by noon the next day. Is that legitimate? Yeah, it's legitimate. It's legitimate. It's within the bounds of what someone would reasonably expect based on the FedEx website, right? Now, there's lots of other cases which are not. So, ladies and gentlemen, this has several implications. One is signatures. I mean, if we have a method that in the supertype takes certain arguments, the subtypes for that supertype need to have the corresponding method take certain corresponding sets of arguments. So if T1 is a subtype of T2, so if we have A as a subtype of B, so T1 here is A and T2 is B, then T1 should be equally or more restrictive than T2. So in terms of the arguments it can take, here it can, okay, so I've got to be, okay, sorry, this is just laying out relationships between types. So string, we say, for example, is more restrictive than object in the same sense that I've used here with these sets. If we have all objects, strings are a subset of them, right? We consider all objects, right? In Java, strings are a subset of objects, correct? Yeah? So I'm just defining sort of what it means for something to be more restrictive. We're thinking of it in a set theoretic sense here. Okay, so the signature rule here is that subtypes must have method signatures that are compatible with the subtypes, okay? So for parameters in a subtype, if we have a method zap in a supertype and subtype, so we have a method zap that in B and then in A as well, okay? If zap in the supertype B, if it accepts something that's a string, for example, let's be a little bit more creative than this. If it accepts in a set in for zap in the supertype, and accepts some set, would it be legitimate for A to only accept, in A, the corresponding method zap, to only accept hash sets? And for the others, it just won't work. Would that be legitimate?
No,
No. Why not?
because you're strengthening the precant.
Yeah, you're strengthening the precandidate. You're making it more restrictive what it will handle. And to be very concrete about it, if secretly we had a B in foo, and we call B dot zap, right? And we passed it some sort of set, S, some sort of old set that happens not to be a hash set, we could legitimately think that, well, zap takes any old set, and if secretly this were an A, and it said, sorry, I don't deal with anything but hash sets, that would be a big problem, because when foo was written over here to operate on B's, we didn't even know that A would ever exist. And suddenly, we have this thing A, which is saying, I don't accept all sets, I accept hash set, but I can be passed around as if I'm a B. I mean, that's a strange thing. So the point here, that would cause someone reasonably to object, right? Reasonably to raise concerns. So the point here is the subtype method parameters, the parameters that these methods take in the subtype, can be no more restrictive than those of the supertype. By contrast, could we allow in principle zap to take objects here? It can accept any old object. Would it be okay if we could call secretly, if we knew it was an A, we could call it, if we knew it were an A, was an A? Yeah. Subjunctive normally I think it's used if it's a possible thing, but yeah, I think Connor's right. It really was. If we knew it was an A, were I to know it were an A, and I were to call zap on it, I could pass it any old object. Would that be okay? Yes, as long as it can accept a set, that's fine. If we're passing it around as if it's B, we pass it a set, it needs to work fine. If A within the subtype actually accepts more types of things, that's okay too. Incidentally, Java doesn't, does Java allow this?
No.
If you say, if this thing overrides app, no, it doesn't allow it. Scala, you can have this sort of covariance, or contravariance, as we'll see. You actually can allow for flexibility of that sort, okay? So this is basically the same principle about accepting packages. We need the subtype. In terms of preconditions, and parameters are part of preconditions, we need the subtype to be able to accept a broader set or the same set of preconditions as the supertype. We can't have it artificially restrict. So A, the subtype, cannot say, my Zap only handles hash sets, so it's only a small subtype of what people are counting on reasonably for the supertype. That would be like saying my FredX franchise requires you to submit things by 9 a.m., whereas from the website for FedEx you're counting on 12 p.m., okay? So by the same principle, if you're accepting parameters, they cannot be more restrictive than the corresponding parameters in the supertype. Does that make sense? So we want to be able to call that method on something that's secretly the subtype without it blowing up on us. We know for B, the supertype, that we can call Zap on any old set, type-wise, and so we need to be able to do that for the subtype. If it wants to take more things, that's fine. That's its business. If we're treating it like a B, we don't even know about that. It's only if we're treating it as an A that we could take advantage of that flexibility. Okay, now, the plot, ladies and gentlemen, thickens. Because if we have return types, we have the opposite type of issue, because these are about post conditions, right? So subtype method return types can only be the same or more restrictive than those of subtype. So if Zap up here in the supertype returns an object, or let's say it returns a set. Could we in the subtype return any old collection? Could someone be rudely surprised if what they think they're going to get back is a set, and it turns out it's some collection? You know, it's a hash table, or it's a vector, or it's an array. Could they be rudely surprised if they're counting on this being a set? Yeah, they could be rudely surprised. But they think they've got a B, and they could study the interface for Bs and say, you know, there's no way that's going to return anything but a set. But secretly they're given back an array buffer. Could they be reasonably surprised? Yeah, they'd say, like, you don't give me something that's a set. I can't call set operations on this thing. You give me back some old collection. So that would be bad. That would be bad. We can't. That would be like us saying, sorry, Smurf Red X, we only guarantee delivery by midnight the next day. That would be like saying, you're going to be on a flight which gets in at 10:30 and it actually gets in past 1 a.m. Yeah, that would not be a good thing. Okay, I can speak from experience. So, would it be okay for the subtype here to return a hash set?
Yeah.
Yeah, it would be. Or a bitmap set. A set that keep track of things secretly using bitmaps, or so that, you know, bits and in the context of a large collection. Yeah, it would be fine. They're all sets, so it's fine. It's just being more specific about which particular set it's returning. So, ladies and gentlemen, I want to highlight the fact subtype methods can return types they're the same or more restrictive than those of the subtype. That's called covariance. But there's contravariant. So let me emphasize where I say covariance. The subtype, okay, can return. So methods in the subtype can return values that are only the same or more restrictive. In other words, only the same type or a subtype of the corresponding return values in the supertype. So the return types for these methods, if you have A as a subtype of B, the return type for the corresponding method in A can be a subtype of the corresponding method in B, including the same type. Okay? So subtyping, if it's a method in a subtype, the return type can be a subtype of the return type of the corresponding method in the supertype. That's why I say covariance. They vary together in the same way. By contrast, for parameters, it's contravariance. It's the opposite. You know, supertype can take in a parameter. If we have A as a subtype of B, and we have a method in A corresponds to a method in B, if we consider the parameters for that method, the parameters for that method in the subtype, ladies and gentlemen, can only be supertype of, including the same type, as the corresponding parameters for that method in the supertype. Okay? So there, if you've got a subtype, the parameters can be more general. It could be a supertype of the corresponding parameters of the corresponding method in the supertype. So it varies in the opposite way. That's why it's called contravariance. As we get more and more subtypes underneath, we go deeper and deeper in the subtype hierarchy. The parameters can grow, to higher and higher levels of supertypes. That's why it's contravariance, not covariance. Covariance, they vary together. Okay, and I would just note for return types, if you're dealing with exceptions, the same principle occurs for return types. They're parts of postconditions, so they can only be the same or more restrictive than those of the same supertype expressions. So Java doesn't currently really allow you to take advantage of this. Scala does, and some other languages do. Okay, so here we have some examples of this, and they've illustrated some of the same principles. I want to get to examples today, some added examples of concrete things. So I'm trusting that between the videos and my comments on the board, you've gotten a sense of it. But I've noted that there's some legitimate subtypes. Like this is a legitimate subtype. Process takes something that's less restrictive than the corresponding parameter here. It's a precondition issue. But then there are some that are not legitimate. Like here, if this returns a string, for example, we can't return any old value down here in the subtype. We need it to return something that's a string or more precise. Okay, the second major thing is that the methods need to behave in ways. So that's all about just the typing. I mean, this is just about the types of the arguments. But what's more fundamental than that is that they have to behave consistently. If you have a method square root within the subtype, it has to behave in a way that's consistent with its specification in the supertype. It can't perform a cube root. If you're counting on it, compute a square root in the supertype. If I know if I have a B, I call it, I'll get back something within a certain distance of the square root. I can't then go in A and define that that's actually a cube root and then pass it around as if it's a B. Could that break code? Imagine some mathematical code that's counting on this taking a square root as if it's a B, and you pass it in A that actually does a cube root. Yeah, I mean, that code could be totally messed up. someone's counting, and they say, how can this be possible? I studied this code, it should work perfectly, given the definition of B. You say, well, that's not any old B. This is my special B, just like Fred X. And they could say, that's a fraudulent B. You're not a real B, you're a fraud. A, right? Yeah, so someone could be quite unhappy with that. You could say, you've screwed up my code. You've introduced defects into my code that weren't there. So here, we need these methods that can be behaviorally the same. And what this means is the same principles we've just heard for preconditions. It can weaken preconditions. It can handle a broader set of possibilities, and it can strengthen postconditions. Okay. So maybe this is going to strain credulity. Maybe in the supertype, all we guarantee is that it will operate correctly for perfect squares. There's no guarantees outside of that. For perfect squares, if you pass it a perfect square, it guarantees it will return something within a certain tolerance level. And A perhaps defines square roots for all positive numbers. Or maybe it handles, in the supertype, it says the precondition is that you have to handle a number that's greater than or equal to 0. That's a precondition. Subtype for square root might loosen that. Say, no, it'll handle other cases as well. That would be acceptable. And then for postconditions, maybe square root in the supertype guarantees returning a value within a certain distance of the square root, and the subtype uses extra sophisticated algorithm to get only half of that level of error. It still lies within the expectation, so it's fine. Okay. Same basic rules. Okay. Now the third component here is the subtype. This goes beyond methods alone. The subtype has to preserve properties of the supertype interface. Notice these first two, ladies and gentlemen. If this didn't strike you from the video, these first two have to do with method. You can focus on each method in isolation. I could focus in on this method or that method. Well, if I were taller, I could focus, right? I could just focus on a given method in isolation, the zap method, and I can assess it. Signature compatibility, in other words, are the types consistent, contravariance and covariance, and does it behave in this way? This last one, I want to emphatically say, in fact, I'm tempted to shout it, but I think it would disturb people outside the classroom. This last one is about not just one method in isolation, it's about the emergent behavior that can be expected from multiple methods. Okay? The subtype interface as a whole must preserve properties of the supertype interface. And this means any collection of calling different methods. Okay? And by the way, these last two require specifications to reason about them reliably. They require some statement as to what these methods do. Okay? So the properties here, it goes beyond methods in isolation to talk about two additional things. Invariants. Things that are true at any given time, they have to be true. Is the value associated with this quantity is always 0 or more. That's an invariant. This data structure never contains a null key. Invariant. The data structure always has size greater than 0. Invariant. That's an invariant. Something that's true at any one time. Any one time you could freeze time, check. Is this true? Invariant. There's also a thing with history properties. These are properties that if you consider them at time 1 and time 2, where without loss of generality, we'll consider time 2 at a greater than or later than time 1, the property has to hold between those two times. So it's not something you can count on. You could just assess it at any one moment. It's something that's holds between 2 points in time. Give me an example of a history property. Maybe the most sort of prototypical history property. It's one I've actually mentioned several times in this lecture. It's that an object doesn't
change, it's immutable.
It doesn't change, it's immutable. That's a history property. You can't assess that at any one time, but if you only look at one time, you don't know what it was before, so you can't really check did it change. But a history property is something that if you look at time 1 and time 2, they should be the same, right? And the point here is that with these history properties, well, with these properties in the sort of third criteria here, these provable properties, these are things that go beyond one method, any one method. It's about the collective behavior of a bunch of different methods. How can they? So if you look at, you're considering the supertype B, and you're looking at its different methods, you say there's no way this can change. There's no method that changes this thing. There's no method that is going to change the values here. Then you could reasonably say, okay, this thing is unchanging. I don't need to check its value on an ongoing basis because I know once I've checked it once, it'll always have the same value. I don't need to check it again. I've done a test. If this is the case, I've done that once. From now on, it's going to be the case. We can't now have A, start allowing it to change willy-nilly. Okay. So if you have a supertype, for example, that only supports inserts, you can't in a subtype now say, well, I'm going to reuse some of that code, but I'm going to support deletes as well. Sorry, if that can be passed around as if it's a member of that supertype, someone could be rudely surprised because they're counting on the fact that it never decreases in size, or if a value's in there once, they don't have to check again. And suddenly, what they've got is an A, and things are being deleted from it elsewhere in the code base, and you keep on seeing it, and you say, well, it can't change that way. Okay, so here's some examples, right? Okay, so here's a base type. We have a counter object. These are toy examples to communicate the principles, but they carry over in a big way to real examples. We have a get, which gets the value of that counter, and an increment method that increments it. I'll leave it at that. Could it be better specified? You bet it could be. Okay, so here's counter 2. It claims to be a subtype of counter, but here we define increment. So the effects of increment, by the way, this is another way of specifying post conditions. It's used in the Liskov and Subtype, great book on program development in Java. Here, increment is defined as basically doubling the value. Is that a legitimate subtype of counter? Could someone, if they had something they thought was a counter, they think it's a B, super type, but it's actually a counter 2, and they call increment. Could they be rudely surprised?
They could be even more rudely surprised when they realize there's no get function.
Well, no, that's just not overridden. So I should say this extends counter, let's say. So you're using the get from up there. But they'd be pretty rudely surprised if they realized that there is something that is sort of strange about counter 2. What values can counter 2 take on? Zero. If you double it again, you get what? Zero. Whereas someone could reasonably, from counter, conclude that it can contain values other than 0. I mean, increment. But there is a problem here in the sense that increment should really be defined. So this says increments. Really, it should say by 1 or something like that, because it's a bit loosey-goosey. But I think you could say with confidence, and this is just about the thing, ladies and gentlemen. Look, we live in an imperfect world. Specifications have some ambiguities. Try as we might to try to eliminate them. But we can at least avoid ambiguities big enough to drive a truck through. We could at least avoid huge ambiguities. And one huge ambiguity, or one big problem that we can avoid here is, one big problem we could head off. We could say increment surely doesn't mean double. So if someone has a counter 2, they could be rudely surprised. They think it's a counter 1. They could say, this isn't a counter. If I increment this, it's not increasing. Right? It's certainly not increasing in a sensible way. So this is a problematic subtype. And you could say, yes, it's imperfect, but it's a problematic subtype. Okay, let's consider counter 4 here. Counter 4. Counter 4 extends counter. It has all those methods, and in fact it reuses their definition. But here we have a new method called double value. And this doubles the current value of the counter. Is that okay? Is this a subtype?
Yeah.
Yes. If you had a counter 4, something that was secretly counter 4, you just thought it was a counter, and you were behaving, interacting with it as a counter. Are there any occasions where you'd be incredibly rudely surprised? You'd say, this is impossible for a counter. No, because basically an object of counter 4 type passed around, if we call increment on it, behaves perfectly normally, as we would think. Call get on it. Any value we could get through counter 4, we could also get through a counter, right? If we have the value 8, could we get it through a counter? Yeah. Starts at 0 and you call increment. Like you continue, but call it 8 times, you could get a value 8, and that's alternatively, we could call it once, called double value. Secretly elsewhere in the code where we know we're dealing with a counter 4, we could double, and get an 8, right? Right? But any counter 4, it behaves in a way that's indistinguishable from the standpoint of someone operating with a counter, but it offers extra functionality, right? Yeah, it offers additional functionality. So it is an okay subtype. This counter 2 is not. How about this guy? Counter 3. Counter 3 claims to be a subtype of counter. Maybe it extends counter, for example. But it allows another type of constructor that allows you to pass in any integer as the starting value for the counter. Is that a legitimate subtype?
What if you pass
not
in a
quite.
negative?
Yeah, pass in a negative, that would be impossible to get through this, right? So someone in the code using a counter might reasonably conclude, might optimize their code, some tight loop or whatever, for the fact that counter is always 0 or more. And maybe they use it as an index into an array or something like that, right? And suddenly they're getting a negative value that could be passed into them. Could break their code. Their code hard codes an assumption, perhaps, that it's greater than or equal to 0. Now, if they're savvy, they might assert that, prevent problems, but even then, it would only show up at runtime that this assumption is violated. But counter 3 could be passed in with a negative value, and they could say, this is impossible. I can't possibly get a negative value out of this. Right? And they could be rudely surprised. If something that's passed in as a counter 3 is the A here, it's being passed in as if it's a counter B, and some method that uses it, all you know is I've got a counter, secretly you've got a counter 3, and you say, wait a minute, there's no way I could have a negative value. Given the definition of counter, there's no way. Again, maybe counter was created years before the counter 3 interface. No one foresaw that there'd be a need for a negative value. So counter 3 is not a legitimate subtype, ladies and gentlemen. How about counter 5? Next time you're in RUH, and you're waiting in that line for the inpatient admitting, and they say, go to counter 5. Maybe you'll think of this. Is this a legitimate subtype? Yeah, I wish I could pull this up. Physics doesn't work that way. So ladies and gentlemen, does counter 5, is that a legit subtype? People in the back, you could stand up. I won't take it as a standing ovation. Is counter 5, is that a legitimate subtype? So here, it claims to be a subtype of counter, but it has a decrement positive. So it has a precondition that it can only be called if the values are, if the current value is greater than 0. And if that's the case, then it will decrement the value of this. So it will decline. It will go down by 1. Is that a legitimate subtype of counter? No. Why not?
Well, in this case, it says that get has to be greater than 0, but the constructor sets it to 0.
Okay, that's true, but actually I would say that's not a problem. That's just saying under what conditions can this method be
Well,
called?
but couldn't somebody assume that it's using counter, assume that they can call get on 0, in which case it would fail out?
Oh, they could, but okay. So this gets, it's great thinking, Alan, here, but it gets to a very key issue. So one of the ways you want to think about this, mark my words, this is going to be really helpful for your final exam if you can master these skills, okay? Ladies and gentlemen, when you're looking at these examples, you should be asking yourself a couple base questions. One is, the most fundamental is, could I be rudely surprised? If I thought I had a counter, could I be rudely surprised by counter 5? Okay? But one thing that you should be asking here as a step towards that is, okay, what does counter 5 give me? You'll notice that counter 5 is different than counter 2. Counter 2 actually overrides increment, right? Counter 5 doesn't in fact override increment. It just adds an additional method, right? Now, if you had a counter, if you had something that's, if you thought you had just a regular counter and all you knew about was get and increment, are you going to know to call decrement positive? No, because it doesn't seem like this. But there is so in short, someone who has a counter, they're not going to be calling decrement positive themselves, but there is a problem. Maybe you're onto this.
Oh, well, I was just saying, can I reevaluate my statement? Because
Yeah.
from my perspective, I can't see the comment on requires in front of get, so I thought get was being overridden.
Oh no, I'm sorry. Yeah. Physics strikes again. So yeah, no, get is not being overridden. It's just it requires is a precondition on this decrement positive. But there is a problem with counter 5. What is it?
History properties.
It's a history property. What can be violated?
Counter can never go down.
Counter can never decline. This can never decrease. Can only stay the same value or not decrease. Could someone be counting on that for code? Yeah, they could. To prove that the algorithm converges or something. And if you've got a counter 5 suddenly, your code, the code of the person who's treating it like a counter will not itself be calling decrement positive, but somewhere else in the code base, it could be calling decrement positive on this thing in ways that interacts with the code that's treating it like a counter. And now it's called decrement positive, and it's going down over time. And that could break their assumptions that once once it's had this value, it's never going to decline, so we know it'll never overwrite an earlier value of the array or whatever. And here it does. And someone could say, wait, a counter can never decline. It's impossible. If I looked at this interface, I could spend hours looking at this interface and reasoning on it. It can never decline. Well, okay. Mumble. Okay, there is this issue of overflow, that if it gets to, to a value at max int, and probably I should tighten this up to prevent that. But basically, it should never decline in sort of colloquial terms here. Okay, and I should really increase that. Okay, so this is so just to map these out. This one is bad because it violates a history property. It can decline, whereas this can't. This can lead to violation of an invariant, that it's greater than or equal to 0 at all times, which is a property about this. Notice that these two properties, history property and invariant, that's not a function of any one method here. It's a collective emergent property of this whole thing, that it can never be less than or equal to 0. It can never decline. Right? That's not about one method in isolation. It's about the constellation of methods, how they can interact. Counter 4 is a perfectly legitimate subtype. And I want to come back to the Allen question. Or the Allen sort of discussion here. Because one of the tricks you're going to want to master here is, look, counter 4, all it does, it adds a method here. The method is just it does things that can already be accomplished with these methods, just in a more perhaps convenient way, like a double set. It's not going to break it. It's not going to break what's going on here. It just provides another way of getting access to this functionality, but in a more convenient way. It doesn't break that supertype. You should be looking especially for cases of overridden methods, because those are cases where now you're going to be able to focus in, is this behaviorally compatible? This one here with the increment being defined to double something, it's not behaviorally compatible with the supertype. Okay, so those are some examples there. Let's go into more examples, right? Okay, so yeah, tips. Ask whether there's any way a user of the apparent class could be rudely surprised. Well, we'll come to this issue. Be wary of subclassing based on desire for code reuse. Subtyping, ladies and gentlemen, and subclassing by extension are not ways of reusing code predominantly. They're ways of achieving polymorphism. And as we'll see in this class, there's better ways using what are called mix-ins and traits in Scala to achieve code reuse without implying all these things with subclassing, particularly for mix-ins. Okay. Okay, and we need specifications to reason reliably about these things. Okay, so I'm going to focus on some more examples. Okay, so here's counter. Favorite counter. Here's my counter 2. So my counter 2 has a constructor that initializes the counter to hold 0, just like the original one. But it has a reset. There's a method called reset. You pass it a value, an integer value, and it will reset the counter to that value. Is that a legitimate subtype of counter? Because basically reset is like set.
It violates the history condition.
Yeah, it violates the history property. It could lead it to decline. What else could it violate? Could violate an invariant.
Down.
Yeah, that it's set to negative value. Remember, an invariant is something we can assess at any one time. and a property of that sort will be that it's always greater than or equal to 0. Can this one here can counter by itself? If I were just operating use off of the definition of counter, could this ever be less than 0? Could I ever have a value less than 0?
No.
No. No. Something I could assess at any one time, calling get, is this less than 0? I could assess it, right, in a very straightforward way. But it's a property about it at any one time. But my counter 2, could I arrive at something that's less than 0? No? Oh, man, I'm sorry. I stand before you remiss. I stand before you negligent. And in fact, because of the precondition, we can't violate an invariant. This purely violates history properties because there's a precondition for reset that you can only reset it to a value that's greater than or equal to 0. So this will never violate invariant. It will violate it, but it could violate the history property. If that precondition were gone, could it violate the invariant? Yeah, then it could be less than or equal to 0. Okay, how about this one? Dual counter. Here I have 2 counters, counter 1 and counter 2. Okay, it extends counter, so it's a subclass, and by implication a subtype. It can be passed around like a counter. And I can call get, returns the value of the first counter. Get 2, value of the second counter. I can have increment, increments counter 1, increment 2, increments counter 2. Okay, dual counter. Let me ask this. Is dual counter, so put aside the thing on the right, is dual counter a legitimate subtype of counter? Yeah, it's a pretty legitimate subtype. It's a nifty subtype in my book. So, ladies and gentlemen, I mean, there's a nice little extension to it. Nothing that this does. If you had a dual counter secretly being treated as if it's a counter, it would behave perfectly reasonably. Secretly under the covers, it's a dual counter, but you don't know it. Somewhere else in the code base, it could be calling get 2 and increment 2. It wouldn't bother the functionality of the counter, right? Perfectly legitimate, perfectly fine, perfect behavioral subtype. And here's the Liskov substitution property with respect to counter. So how about, however, swappable dual counter? Why not?
It could go
Because
down.
it could go down.
It could go down. You swap the 2 counters, now suddenly counter 1 could go down. So if you just knew that the swappable dual counter was a counter, suddenly it could decline because somewhere else in the code, who knows it is a swappable dual counter, they call swap counter values. And suddenly the value of your counter is dropped precipitously, right? That would be adverse. Okay, I'm gonna
Would it violate the history property or?
history property. Yeah, history property. A dual counter and a swappable dual counter can't go less than or equal to 0, so it wouldn't be violating an invariant. Okay. Okay, how about final one? Inset. We have an inset. Inset allows insert, remove, is in, size, elements, subset. It asks whether one set is a subset. And then we have, consider an int bag. Identical except it maintains information on multiple inserts of identical integers. So if you insert the same integer twice,
It knows there's 2 of them.
it knows there's 2 of them. So if you insert it twice and you remove one, it will still be there. Yeah, the remaining one will still be there. Is that a legitimate subtype of inset?
Depends how you implement it. If you implemented it like a real bag, it wouldn't be. But if you implemented it as if I remove 2, I remove all 2s, but I want to know how many I added first, then it would be fine.
Any thoughts on that?
Because it says it only maintains info on multiple inserts, so that could mean that remove gets rid of all of them.
Okay, so suppose remove did not get rid of all of them. Suppose remove only deleted them one at a time.
Then it's not a set anymore.
Okay, and could someone be reasonably surprised if they have one of, they think they have an inset and they actually have one, an int bag that you insert two, and then you remove, and they call remove to remove one, and they say, oh, there's still one remaining. Could they be rudely surprised?
Yeah, because they thought it was a giant
Yeah.
switch table, and now it's not.
Yeah, they thought it was an inset, and they expect to remove. Well, remove something that's in there. It should no longer be is in after that, and now it is, but it's still there. Suppose int bag. I'll leave you with this, and I'll let you think about it for next time. Suppose int bag were to remove all. So when you call remove on something, it removes all evidence, all of them from there. So it allows you to insert it more than once, but it removes all of them. Would that be a legitimate inset? That's my question.
Yeah. Because it's still idempotent on add, it's still idempotent on remove.
There is a size method.
They'd have to call it.
It's cardinality, which means the size of the set. Okay, so I'll let you think about this. Okay, we'll finish up with some examples next time before we go on to say some classing and mix-ins and traits in Scala. Okay. Okay. Cool.